Hello, Dr. Ahmed. Our presentation today about non-structural walls, and it's titled as Effect of Non-Structural Walls on High-Rise Building Response. We are going to talk about these following outlines. Firstly, introduction, and then modeling of non-structural walls, effect of non-structural walls and soft story, modes of failure of non-structural walls, effect of non-structural walls on structure response to lateral loads, and finally conclusion and references. As an introduction, non-structural walls play an important role on lateral stiffness and strength of all buildings, especially when it comes to high-rise buildings in high seismicity region. Over years, many earthquakes have naturally occurred and lead to severe damages and cost people's life due to the failure mode of soft story. The irregularity of non-structural walls has significant effect on creating weaker floor than the others and finally leads to total collapse of building. When it comes to modeling of non-structural walls, infill panels change the mechanism of the structure from frame action to truss action. The infill walls can be substituted by an compression and tension struts. And here we can see in the next video here the infill wall create compression strut as a diagonal member, as we can see.
Non-structural walls and soft story. Nowadays, having open ground floor is common. As shown in the figure, clients usually need to parking in ground floors or reception or make it as a lobby. And in these cases, the structural engineers are generally neglect or ignore the stiffness of the infill wall during the modeling, which considered as a big mistake. There is a large effect to neglect the stiffness vary between floors due to infill masonry walls because the upper stories will move as a single block with a small displacement as shown in the figure, but the ground floor will move with a large displacement because of the soft story effect, which will affect with the severe stresses on the vertical element. During the earthquake, bending moment and shear strength will increase on columns, beams in the soft story than the ones in the upper story. And if the columns are not capable to resist the shear, they may be damaged or lead to collapse, as shown in the figures. Actually, to avoid this soft story effect, we must take into consideration the stiffness of the infill wall during the modeling, by modeling it with the equivalent strut as follows. The equivalent strut area is equal to the strut width multiplied by the thickness of the wall, and the strut width is equal to 0.175 multiplied by lambda by h power negative 0.4 by d, and the lambda is a coefficient depending on properties of the infill. We are only doing that to take into consideration the effect of the infill masonry.
Now we will talk about failure modes of infill panels. Mehrabi et al. Conducted several experimental tests on single bay frames with infill walls. The main failure modes identified by Mehrabi et al. Are mid-height sliding, as shown in figure A, diagonal cracking, as shown in figure B, bed joint sliding, as shown in figure C, corner crushing as shown in figure D. Also, Wael Dakhakhnī et al., after several experimental and analytical studies, found 5 main modes of failure. Corner crushing mode, which represents crushing of infill in at least one of its loaded corners as shown in figure A, which is usually associated with infill of weak masonry blocks surrounded by frame with weak joints and strong members. The next mode is sliding shear mode, which represents horizontal sliding shear failure through bed joints of a masonry infill, as shown in figure B. It's usually associated with weak mortar joints and strong frame. The next mode is diagonal compression, which represents crushing of infill within its central region, as shown in figure C. It is usually associated with relatively slender infill. The next mode is diagonal cracking, represents a crack connecting the two loaded corners, as shown in figure D. This mode is associated with weak frame or frame joints and strong infill. The next mode is frame failure mode, which represents the formation of plastic hinges in columns, as shown in figure E. It is also associated with weak frame or frame joints and strong infill.
First, I'm going to talk about the effect of non-structural walls on a single-story structure. Richardson, in 1986, conducted several experimental and analytical tests on a single-story structure. He then plotted the load deflection curve, which shows that the fully infilled frame could carry lateral load up to 5 times the bare frame. Mimari, in 2018, compared the results obtained by Richardson with a model where the infill walls are isolated from the structure using a fuse element. As shown in the load deflection diagram, this model can resist up to 3 times the bare frame. Now I'm going to talk about the effect of non-structural walls on a multi-story structure. Pandis et al. In 2016 studied 4 different models of 11-story buildings. The first model was a bare structure with no masonry walls. The other 3 models are infilled with 40% masonry walls, but with different configurations. The results he got can be summarized in this diagram, which shows that the infilled structure exhibits lower top story displacement, lower time period, and attracts higher base shear than the bare structure. Also, different configurations of masonry walls alter the structural response to lateral loads.
In order to assess the effects of non-structural walls on high-rise buildings, a finite element model was made using ANSYS 10.0 software for a building with a planned dimensions of 30 meters by 30 meters and a total height of 90 meters. With 5 different combinations of structural components and non-structural components that can be listed as follows. First, the skeletal frame without adding any non-structural components to it. Second, the frame but after adding infill walls. Third, the shear wall frame with openings at the midspan in the shear wall at each floor. Fourth, the shear wall frame but with windows. And finally, the shear wall frame with glass facade covered by aluminum frame. There were 4 main assumptions that were made in this model that can be listed as follows. First, it was assumed that the building was symmetric. Second, any non-elastic behavior of materials was neglected. And third, the role of steel reinforcement in concrete was ignored. And finally, no dynamic loads were involved. Only static point load were applied along one side of the building. It was found that the presence of infill walls caused the structure to have an increased stiffness by 60% when comparing the bare frame with the frame with infill walls. The effect of windows on the inter-story drift was about 1.2%, which was not significant when comparing the shear wall frame with the shear wall frame with windows. The glass curtain wall increased the building stiffness by almost 12% when comparing both the shear wall frame by the shear wall frames with facade.
To summarize our presentation, the infill panels for masonry walls change the mechanism of the structure from frame action to truss action. There are several methods that can be adopted to model non-structural walls. There are several modes of failure in non-structural walls. Non-structural walls can contribute in the soft story mechanism of the structure. The presence of non-structural walls in high-rise building decreases the top story displacement and time period of the structure while the base shear increases. These are our references, and thank you.